Welcome back to the classroom. My name is Mr. Wong. Today we're going to be looking at relative velocity in one dimension. We're going to be covering the following dot point: calculate the relative velocity of two objects moving along the same line using vector analysis. But we're looking at the calculation problems. If you haven't looked at the theoretical lesson yet, I would recommend you to try that first. But this lesson will all be about the calculations of vectors in one dimension, or relative velocity in one dimension, I should say. Okay, so let's go with our first question for this part of the recordings. So we have two trains passing each other. The first is traveling at 110 kilometers per hour west. Let's call that the negative direction. And we have a second one that's traveling at 90 kilometers per hour east. Let's call you the first, or the positive direction. It says calculate the velocity of the second train relative to the first. Let's firstly draw out our vector arrows. So train 1, we'll call you here, is traveling at 110 kilometers in the west direction. And over here we have train 2. Notice how the arrow is a little bit shorter because the speed or the velocity is a bit slower. That's train 2, and it has traveled 90 kilometers per hour. So same thing as always, we need to work out what the frame of reference we're trying to base this on. We want to look at the first train. So we're looking at the frame of reference of this fella up here. So train 1, okay, from train 1's perspective, if 1 hour has passed, if I add the vector arrows together, it would appear that train 2 has moved 190 kilometers away from it within that hour. Okay, so that's what we see. Because I said that east was the positive direction, or this one here, train 2's perspective, or from train 1's perspective, train 2 has traveled plus 190 kilometers per hour away from it. Okay, the next set of equations, or the next set of questions, sorry. A truck is traveling east at 60 kilometers. Let's say that's the positive direction. So our truck is traveling at 60 kilometers east, is overtaken by a car traveling at 80 kilometers in the same direction. So in this here, we have 80 kilometers, and we have our car in this direction here. It says calculate the velocity of the truck relative to the car. So the bit we're looking at, or the frame of reference, is the car here, and we're looking backwards to where the truck is. Now, if we let 1 hour pass, the truck has gone 60 kilometers, the car has gone 80 kilometers. So according to the car's perspective, the truck is behind it by at least, or not at least, but exactly 20 kilometers. Now, because the arrow is going backwards, it's a negative value, and because it's after 1 hour, it would look to the car as if the truck is traveling at 20 kilometers per hour negative in the opposite direction of it. It sounds weird, like I said before, but if you imagine this car moving forward and this car being behind it, every time this car is looking behind itself, the truck will look like it's moving away from it at 20 kilometers per hour, or behind it at 20 kilometers per hour. Okay, so that's how we deal with that. And let's try another set of questions. Okay, although this one says question 6, it should actually be question 4. So I'll just correct that. So a car is traveling along a road at 20 meters per second. A truck is traveling in the same direction, 100 meters ahead of it at 18 meters per second. So they're both moving, let's say, moving in the positive direction. Okay, cool. It says, how long would it take for the car to overtake the truck? So we need to firstly look at the relative velocity between the car and the truck. So the car is moving in this direction here. The truck is moving in this direction here. So the car takes 20 meters per second and the truck is 18 meters per second. Okay, so in order to tackle this question, we need to look at this in the frame of reference of the truck. Okay, because the truck will tell us, because they're moving in the same direction, so we need to find the relative velocity here. Or in this case, it doesn't really matter, I guess, because the value would be the same, but it would be helpful regardless. So if we have a look at the relative velocity between the car and the truck, the car is clearly moving at 4 meters per second faster than our truck. Okay? If the truck is traveling at a distance of 100 meters ahead of our car, we can actually plug it into the equation here. Velocity equals to displacement over time. Reason why we can use this formula here is because we didn't say that the car is accelerating. So if I have a relative velocity of 4, my displacement is 100 over time. This gives me an analysis of if the car is moving at 4 meters per second faster than the truck, but it's behind the truck by 100 meters, okay, how much time is taken for it to catch up? So in this case, it would be t equals to 100 over 4, and it would take it about 25 seconds to reach the truck. How far will the car have traveled in that time? Okay, so again, using the same formula, this time I want to find its overall displacement. The car has traveled at a velocity of 22 meters per second, because we're looking at the perspective of the car, right? So the car is moving at 20 meters per second. Its displacement is what we want to find. The time taken is 25 seconds. So its displacement equals to 22 times 25, and that's 550 meters traveled by our car in order to catch up to the truck. And that's how you do that question there. Let's try a different set. Okay, so we reach question 5. Consider we have 2 trains. Train A is traveling from X to Y. So let's just say X to Y is going in this direction at 45 meters per an hour, or 45 kilometers per hour. And train B traveling from X to Y, we'll call that the negative direction, at 35 kilometers per hour. X is 32 kilometers due east of Y, and the trains leave their respective stations at 12 noon or 12 p.m. So 320 kilometers due east of Y. Okay, it says calculate the velocity of train A relative to train B. If we have a look, clearly they're moving in the opposite directions of each other as what the vector arrows show. So this time we can actually skip through it because we are quite comfortable with this now. If they're both moving in the opposing directions from each other, we simply just add the velocities together. So 45 plus 35, in which case is 80 kilometers per an hour. According to train B, train A would be moving in the positive direction because we said train A's direction is positive here, okay? If we were talking about direction, then if we actually have a look here, X is 320 kilometers due east of Y. So if we put that as a perspective, X is here, and Y, after 320 kilometers, is in this direction here. So the positive direction we actually labeled here, although it's kind of a bit misleading with the arrows because I didn't actually look into the directions originally, the positive direction is also the west direction in this case. Down here, the relative velocity would therefore have to be negative 80 kilometers per hour, or going to the east direction is what we can say. Remember, if you already wrote the symbols, you don't have to write the directions. This is just more for cross-referencing for those who did show the symbols or use directions instead. And says how long before they actually meet up with each other. So the relative velocity is 80. The distance in separation is 320. And then we have time. Now, because everything is in the same units, I can just leave it. I can just leave everything in kilometers for now, and then I can just change it afterwards. So V is 80 over 320 equals to time. So if I just switch that around, we get approximately 4 hours. Okay, if you want to be really fancy with the times here, then what you can do is times it by 60 minutes, times it by 60 seconds, which gives us 14,400 seconds passed. All right, next set. Okay, so the next set of questions we're going to go into is still one-dimensional. However, we're going to be looking at more frames of references, okay? So imagine if we were on a boat, right? Our velocity of the boat can also be changed by the velocity of the river or of the ocean that it's traveling. Or we can look at a person walking up and down an escalator. If they're going against or with the motion of the escalator, that can also change how fast the object's moving. So let's have a look at these other perspectives. Okay, so the first one we're going to tackle is crossing the river. So river is flowing at 2.5 meters per second, and Sue rows her canoe at 4.3 meters per second. Calculate how long it would take Sue to row a 100-meter course against the flow and with the flow of the river. So if it's against the flow, right, if it's against the flow, she's being slowed down by the boat. So in this case, her relative velocity would be 4.5 subtracted by 2.5, because that's the water pushing against it. And so their relative velocity would be about 2 meters per second. Okay. If I was to then calculate the time taken, time equals to distance over speed, 100 divided by 2, it would take her about 50 seconds to reach that course. If I switched it around and she was going with the flow of the river, that'd be 4.5 plus 2.5, and that would be equivalent to 7 meters per second. So the time taken in this scenario would be 100 divided by 7, and that would take Sue about 14.3 seconds instead. It says, in each case, calculate her speed relative to the water. And in question C, it says, calculate her speed relative to the land. Okay, so I thought it'd be best to show you some vector diagrams when it comes to the part B of that question and part C of that question. So we have a river that flows at 2.5 meters per second, and Sue rows her canoe at 4.5 meters per second. We've already talked about that. What is her relative speed because of the water if we draw out these vectors here? If it's against the flow of the river, okay, if it's against the flow of the river, it's the same scenario as we had when we were saying we had two cars traveling away from each other. Okay, so after after 1 second, if the river was to look back at where the canoe is, it will look as if the canoe has gone 4.5 plus 2.5 meters away from the river, and so the relative speed is 7 meters per second. If we're looking at the canoe when it flows with the river, according to the perspective of the river, the canoe looks to be traveling a bit faster than it, right? Partly because Sue is rowing her canoe at 4.5 meters per second, but also it's also being contributed by the flow of the river, because the river is making Sue move at 7 meters per second overall. So according to the river's perspective, Sue is actually rowing her boat at 4.5 meters per second, and not and not the other way around. A common mistake people might think is they don't account for the fact that the speed of the boat is also being pushed forward by the flowing river. So that's the case there. Okay, so let's go to our last part of the question, and that's what is Sue's speed relative to the land? If we're looking at the perspective of a stationary observer on land and looking at how she's rowing her boat, we can draw the vector diagrams somewhat like this. Okay, in this case, it's simply a subtraction between the two vectors, because remember, the land is stationary. It's not like the river. Okay, so after 1 second, we don't need to do that calculation. It is moving at 2 meters per second against the flow of the river. Okay, if the boat was flowing with the river, or the canoe was flowing with the river, from the stationary person's perspective, the boat has its own velocity, but it's also being pushed faster because of the velocity of the river. And so in that case, it'd be 4.5 plus 2.5, and so we get 70 meters per second. Okay, so I guess the last point we just want to go on is what we've talked about with relative velocity. If we have multiple moving objects or moving perspectives, okay, remember, the boat is a very special case, or moving boat on a river is a very special case, because the river is also a moving frame of reference. It's not a fixed stationary frame. So that can kind of alter the way we see the relative velocities for that. So when the boat is stationary, it will have the same speed as the water, which is sort of why we were sort of saying if the boat was not moving, it still have a velocity of 2.5 meters per second, because the river is still flowing. Now, obviously, if the river's not flowing, then it would have a velocity of 0. When it starts moving, it will have its own speed, but it will also have a speed generated by the water as well. So that's why we have to add the speed of the water component on with the questions we talked about there. If we were looking at the perspective on land, the boat's relative speed would have to be 2.5 meters, would have to be 7 meters per second, sorry, because you will see the water pushing the boat faster as well. Okay, So that concludes our lesson for today. Hopefully, the way we've gone through the questions makes you a little bit more confident of tackling relative velocity questions in one-dimensional plane. And if you found this video useful, give it a like, subscribe, and I will see you next time. Thank you for listening.